My name is Wojciech Kaczmarski, and today we are going to talk about M17 project a little bit. It's a brief description of the protocol, and then after that we are going to focus on the M17 implementation in GNURadio, because we are talking about GNURadio today. All right. So M17 is something that is not really new, because it was created back in 2019 by me, obviously, in Warsaw and in Warsaw, Poland. And it was an answer to a need that popped out in the amateur radio community, because we already have other digital voice modes like the DMR, NXDN, D-Star, and so on. But all of them, or most of them, are not entirely open, which means that even if the specification for the protocol is open, most of that modes don't use open source voice coders. So most of them use AMBE or IMBE, and as far as I know, IMBE is no longer patent encumbered, but AMBE still is. So it's very difficult to experiment with those radios and those modes without touching the voice coder part that is really in the gray area because it's patent encumbered. So M17 is an answer to that problem, and it's completely free, completely open, and the specification is open for everyone and free to download. You can even propose your modification that you would like to see at the application level or the RF level. So M17 is a digital voice mode, but it not only allows to transmit voice, but also data, which doesn't make real difference for the transmission protocol, because ones and zeros are just ones and zeros. So it doesn't care if the payload is encoded speech or just a file. So everything, so you have to actually tell at the application level what are you doing if you are transmitting voice or a data stream. So M17 uses 4FSK at 9600 bits per second, which is not very fast, but allows for very good quality audio, very good quality speech, to be precise, because audio is not really supported by M17. And that's the gross bit rate. That means the error coding is already there, meaning that the actual data rate is 3200 bits per second. And we actually have 2 transmission channels in the RF stream. And we also have stream and packet modes. So if you are familiar with APRS, which is Automated Packet Radio System, APRS, this is something similar to APRS, but we use 4FSK instead of AFSK. And we've got a lot more correction coding going in the protocol. Yeah, so it's payload agnostic, and you decide what's the payload at the application level. Then the specification is, of course, released under GPL 2.0, which means that you are free to share it, print it, use it, whatever. So that's this slide. Now, we've got plenty of implementations already working in the wild. So looking at the upper left corner, we've got an HackerRef that you are probably familiar with. It's an SDR radio, right? So that's a HackerRef transmitting M17 using GNURadio, using our old approach that I'm going to discuss later. And in the background, there is SDR++ decoding the M17 RF stream. Then lower left, those are 2 handheld radios. Exactly, those are this type of radio. And this is an off-shelf DMR, so digital mobile radio handhelds. And those normally only support FM and DMR. So the problem with that radio is, of course, it doesn't do M17, and it's not very easy to. It wasn't easy to tweak the firmware to do anything, to make them do anything else. So we actually, there is a team in Italy, in Milan, called OpenRTX. That's their logo. And they have actually came up with the way of hacking those radios and the way to upload our own firmware. So you can run arbitrary code on those radios and enable it to transmit and receive M17, which is nice because that was the first radio to receive and transmit M17. After a small hardware modification, unfortunately, but the modification is very simple. It just requires to solder 2 Kinner wires, basically, and a resistor. Yeah, so you have to open it up and then modify it. Then we've got something called ZoomSpot. This is not open source. This is actually, I believe it's proprietary. This is an access point. It's a shield for a Raspberry Pi. I bet you know what Raspberry Pi is. So this is actually used to receive and transmit M17 signal over RF and connect it to a reflector. And the reflector is something like a server that runs in the internet somewhere, and many different reflectors can be tied together like a network. So if I had a module like this and someone else at some other place on Earth had something similar, we can talk using M17, using radios like this. So this is just an access point. And it also supports most of other frequency modulated FM-based digital modes like the DMR. But M17 is a new addition to that, so it works with M17 too. Then we've got module 17, which is a baseband processor. It's open source, and me and Mattis DB9 MAT designed it. I did the schematic, and he designed the board. So this is actually used, I don't have a radio with me, but you can take basically any 9600 baud capable radio and connect this module to it to enable it to transmit and receive M17. So this is baseband processor, right? So you connect it using 4 wires, including ground to a radio. So you need to connect the baseband in, out, the PTT signal, and the ground. There is a small display that shows the frequency, but it's just a mock-up. But yeah, you can set your call sign in and just transmit and receive M17. And you also need to connect a Kenwood microphone speaker to it to be able to hear the other side of the RF link, the other party. What else? Then there is a smartphone running DroidStar app, which enables the user to connect something that is of this size. And it's actually something similar to the device in the middle, but it lacks the head that is the Raspberry Pi, right? So instead the Raspberry Pi, you've got the Android app running on your telephone. So this is actually a handheld transceiver, if you like. So you set all the parameters for the transmission on the screen, press the PTT, and then you've got the RF stream going out of the device. And it also receives M17 just fine. And in 2021, I have received a Technical Innovation Award from ARRL for the work on M17. Yeah. Thank you. And last but not least, we have received 2 substantial grants from the ARDC, Amateur Radio Digital Communications, that actually enabled us to do most of these things. Yeah. GNU Radio, finally. So this is the basic setup for M17 transmission using GNURadio, and it uses only M17 native blocks. So there are no out of 3 blocks right here. We've got the file source, which of course has to contain the digital baseband. So we actually have a symbol stream in that file, that binary file. So we've got 4 symbols per byte packed, right? Because every symbol carries 2 bits of data, a D-bit, because it's for FSK. So we've got that packed into a file, and then we of course have to repack that and map to a symbol. So we've got the symbol map right there, 1, 3, -1, -3. This is all based on the specification that is available online. And then that's a very important step because we actually use a square root Nyquist filter approximation, that is the root raised cosine filter, to filter out the baseband, and that's ready to be fed to either a VCO or a block like this, the frequency mode. And after that, you can connect the complex stream to a device like this, which is also probably familiar to most of you, the Pluto SDR. And this is the basic M17 setup that takes the least time to configure and to get on air with M17 using GNURadio. And this was the first method to actually transmit M17. And back in the days, we used to generate the baseband using an input wave file. So you had to record yourself or any source of audio or whatever, generate the binary file, then point GNURadio to that file and run the flow graph. So that was like 2 years ago. Then, after a long time, I have decided to write my own C implementation of the full RF protocol. So from the bit stream that you want to send up to RF. Symbols, yeah, symbols. So we can say it's RF. The source code, of course, is available on GitHub. That's probably the only source code that we publish as a project team. So I have received a few questions about if you can actually use this code in a product. So the question is not very simple because this code was not mentioned to be not meant to be used in a product because it's first it's not optimized, and 2, the role of that code is to be a reference, right? So you can check your own implementation against this one and see if the bit stream is bit exact or not. So that's the role of this code. It's not supposed to be a part of a device available on the market. So after I have wrote that code, I tried this setup, which is, it looks more complicated because we got a stream mux and stuff like that and throttle. But this setup was the starting point for our, mine and Jean-Michel Fried, our work on the GR-M17. So we did this. As the M17 is a digital mode, we in the frame, we don't only send the payload, but we also have some overhead for stuff like who's transmitting, so that's the source, who's the recipient, so that's the destination, and both fields are 6 bytes long, so that's 48 bits for each of the addresses. Then we've got the type field, which is the 2 bytes, then the meta field that most of the time is full of zeros, that's 14 bytes, and then the data, the payload, which is 16 bytes. And you can tell the size by looking at the streammux block. And then after all of that data has been collected and joined together through a throttle, we used to, oh, there is even a date, December 2022. Yeah, so we used to take that stream of file to a named pipe, and then use a compiled code that turned that into symbols. Then we had another GNURadio instance that probably filtered it out with an root-raised cosine filter. And then another program, another compiled code that actually decoded the data. So right here we see that we are decoding payload full of zeros, and the frame number advances from 29, that's hexadecimal, up to 3A. So back then it was a sign that it works, and the CRC is fine, and all of the decoding is fine, including the source call sign AB1CDE, which I believe is fake and doesn't exist. Yeah. Now, this is what we have now. We've got GR-M17 blocks, and that's M17 coder plus M17 decoder. So this is a pair that you can use in your flow graphs to transmit M17 and receive it. So the M17 coder block actually takes 16 bytes per frame as the input. And normally that's a byte vector, which I'm going to show later. And then you have to set the source ID, the destination ID, which normally, because as the M17 is ham radio oriented, but not limited to, we assume that the source and destination are ham radio operators. So normally you are limited to 9 or 8 characters, including dot and slash probably, if I remember correctly. So you can set it arbitrarily. Then type 5 means that it's a stream of voice, stream of compressed speech. Oh, and it's worth noting that we are using free and open source voice coder that has been and still is developed by David Rowe, Victor Kilo 5 DGR, that's his call sign, and it's still under development. So and it's open source, and the guy is a ham radio operator, which is great. Then we've got the decoder, which accepts a stream of symbols as floats, judging by the color, and then the output from that block is the payload. So what we see here is just a loopback. So if we fed the first block with data, we should get the same data at the output. Of course, it adds all the overhead, all the correction coding. So you could actually put something in between to mimic the RF channel. Like you can put all the filters there or the RF channel simulation and see what's the bit error rate and stuff like that. So it's doable. Then we've got the loopback, but it's completed now. So we've got the vector source with the data. That is just a series of bytes, a tuple from 0 to 15. And then we've got the coder with the same source ID. The meta field is just, it's limited to 14 bytes, if I remember correctly. And as long as you don't use encryption, it's not used. Maybe if you want to transmit slow speed data like the positional data from the GPS receiver, you can put that data right into the meta field. So you can transmit your location along with the voice, encoded voice. But if you want to use encryption, you are then not allowed to transmit your location because the space is taken by the meta field, which then is the how do you call that? The nonce field for the AES encryption algorithm. Yeah, then we've got the throttle that is used to slow everything down, so we don't end up with a few gigabytes of dumped payload, as I did once. Yeah, then the symbol stream is decoded back to the file sync. So if you run this, we could expect the file to contain a series of numbers from 0 to 15, just continuing ad infinitum. And indeed, this is what happens. So this is the the hex of that file, of the dump. Then let's do something more interesting. And actually, I can show you a demonstration of this because not all of you were able to reach me at the coffee table. So I've got all the hardware with me and I can simulate this. Well, not simulate, actually run it. So this time we've got the static payload that is just full of zeros, 16 zeros. Then the coder, the throttle that shouldn't be needed in this flow graph because the source is actually dictating what the speed of all of this is. So the scheduler should know what the speed is. But because there is some bug in the code, I'm forced to use the throttle block to make it work. Then we've got the root raised callsign filter and the frequency mode, which is a VCO, fancy. And our resampler, because the symbol stream is 4,800 bits per second and the Pluto SDR accepts like 500K plus, right? So we upsampled that to like 760 something. Then we are also able to transmit encoded speech. The file source should contain just a recording of the speech that we want to transmit. Then we use the Codec 2 block, which is incorporated into the GNURadio already, so you don't have to install anything additional. It's right there. Then vector to stream and packing that's needed to form the byte stream to be accepted by the M17 coder. And then the rest stays the same. After the root raised callsign filter, you can just add a resampler block and feed that data into a Pluto SDR or HackerRef or whatever, B210. This is Pluto SDR is cool because it's a lot cheaper than USRP B210 and it does good work. Here we see SDR++. It's an open source program. And it decodes M17. And it's able to decode the call sign. For blue lines that you see, it's actually, those are symbols. And those are slices at the centers of the symbol. Like if we took the eye diagram for FSK and sliced it in the middle. So we would end up with something like this. And if the signal deteriorates, like the SNR gets worse, you see that the eye gets closer, more closed, right? So there is less space between the symbols. And that causes errors, right? So SDR++ is able to decode actual speech. It's muted in the screenshot, but you can decode speech. Then that's the last slide. So one of the issues is that the coder skips frames. So if I took the SDR, the Pluto SDR, connected it to the laptop and transmitted M17, the problem is that even if the source baseband file is absolutely correct, we would get skips in the audio stream. And I can demonstrate that in just a minute or later at the coffee table. So that's one of the problems. And the M17 decoder doesn't allow for late entries. And the late entry is when there is an ongoing transmission and you suddenly turn your radio on just to listen to what's going on. So the M17 decoder likely, I mean, of course, this is going to be fixed after some time, but it requires some work. So this is work in progress. So the decoder doesn't actually see the sync words that are in the frames. So it sees the first sync word at the beginning of the transmission, and that's it. So you have to first run the code and then start the transmission, because otherwise it's not going to work. And that's it from my side. So thank you. We only have the reference implementation run, and that's GPL. So if that was LGPL, they could have used that code, right? But the problem is that the code is not supposed to be used in a product because it's a reference. So it's like a ruler, right? You can tell, oh, that's 10 centimeters long. So it's only for checking. So if you wanted to write your own implementation, like in Java or something, you can tell, okay, I've got it running, but is it fine? Does it conform with the specification? You could run my code and check, yeah, it did. It works. So it's like that.
Thank you. What FEC are you using?
Forward error coding.
Yeah.
Yeah, we've got two schemes for error coding. We've got the Golay code, 2412 Golay code, that is used for the link setup frame and the link information channel. So that's a side channel that is used to transmit, to carry the information on the destination source and the metadata and stuff like that. Then for the payload, we've got convolutional coding, and that's it.
In your presentation with the Streamux, you could see that there was a lot of overhead. So is it for each 16-byte packet you send the source and destination and type?
Actually, that data is sent over a separate channel. So we've got two separate channels in M17. One of the channels is used to actually transmit the data, the payload, which is 3200 bits per second. Then we've got additional field that is, I believe, 96 bits per frame, and each frame is 40 milliseconds long. And that is encoded using Golay code, and that's it. So there is only the sync word left. So all of that is in the FEC, yeah, basically.
It's not a question. Maybe it's only to ask you why you missed to mention as an application DudeStar, which is without any hardware.
Well, I missed it, but only partially, because DroidStar is shown right here.
Yes, but here you need a hardware. On the DudeStar, you don't need nothing. You can use it. I have it in my phone.
Actually, DroidStar is a new name for DudeStar.
Okay, maybe.
And to transmit M17 using DroidStar, yes, you have to use external hardware. But to connect to a reflector, you don't have it. You don't need it.
Yeah, exactly.
Yeah. So, but then we are somehow moving away from ham radio to voice over IP.
Anyway, congratulations for your work.
Thank you.
The side of ham radio.
Thank you.
Yeah, thank you very much for your presentation. Can you share with us your roadmap? I mean, what's the next milestone, or what do you need from the community, in case you need something?
I think the next one. Well, I'm mostly involved in OpenHT sub-project because M17 is an ecosystem. It's not only the protocol, it's not only the hacking the radios and stuff like that. It's also a big team that is working on many different other things, like the OpenHT, which is going to be an open source handheld with 8086 RF215 chip, which is a complete RF transceiver, IQ transceiver, that would allow ham radio operators to run every mode, basically every mode, even Tetra, with a handheld. And the design is built around that chip that I have just mentioned and an FPGA. So we've got the design ready, the schematic is ready, and now we are working on the board, the PCB for it. So that's our next milestone, I would say. So releasing a handheld that would empower ham radio operators. So you can finally transmit not only frequency modulation based modes like the DMR or just wiggling the VCO, because that's no fun, but we actually want people to access like 16 QAM and higher order transmissions like that. 32 APSK also by Daniel Esteves. Very nice modem.
Thanks, that's pretty cool. You just mentioned other modulations, higher order modulations. What led to the decision to go with an FS4 FSK at 9600 baud? That feels like a strange choice.
It's not strange if you take a look at other modes, because the goal was to be maybe not backward compatible, because that's a wrong phrase, but we wanted to M17 to be like compatible with this. So a user can just take this radio, modify it, and it would work. So 4FSK was the best pick for us, because 2FSK was like, let's say, too slow. 4FSK, it's okay. It's used by DMR, it's used by NXDN and some other modes. So we obviously couldn't use PSK like Tetra, because it's not really doable with this, where you've got just a VCO. So yeah, it was basically based on that approach. So you can actually build a board like this, the baseband processor connected to an existing radio, so it's like compatible with the stuff that people have already.
That's a pretty cool motivation. Thanks.
Thank you.